Welcome everyone to the 9th edition of the Quantum Portugal initiative. Welcome to our speaker who had not to travel this time because we have a virtual event, but originally would have had traveled from University of Sydney in Australia. And we of course hope to welcome Igor another time, hopefully next year at INL in our premises in Braga, Portugal. But for now, we are very glad he accepted our invitation. He is going to give a presentation entitled Hexagonal Boron Nitride, Emerging Platform for Quantum Photonics. And we are excited about the different interactions of single quantum emitters that he's going to talk about. Igor Aharonovich is, as I mentioned, a professor at University of Sydney. He did his PhD in 2010 at the University of Melbourne, and he spent 2 years in Harvard as postdoctoral researcher at the group of Professor Evelyn Hu. In 2013, he returned to Australia and joined the University of Technology, Sydney, where now he is as professor and at the UTS node director of the ASC Center of Excellence for Transformation of Meta-Optical Systems. You will see that his group explores different photonic properties, especially of 2D materials, but also single point defects and diamond. And as our Quantum Portugal initiative PhD students and the community in the field is really excited about the emerging opportunities that the single quantum photon emitters are proposing. We invited Igor and to give like an introduction, a lecture into the field such that the students can follow, but also to showcase his latest research results. And so thank you, Igor, for accepting our invitation, and please, the virtual stage is yours.
Thank you very much, Jana, and thank you for this introduction. Indeed, I was hoping to attend in person, but it is what it is, and so I still hope to, of course, see you all in person, maybe sometime next year. So in today, in the next kind of 45 minutes or so, we'll venture you through our exploration of defects in hexagonal boron nitride, and I'll give you a little bit of introduction into why we are studying them. And I should just say up front, it's mainly a curiosity-driven research. I'm not gonna show you how to build a quantum computer at the end of this talk. So I guess to kind of kick it in, so I think we are exactly at the opposite part of the world, which is down here in Sydney, Australia. So of course, once the borders are open, I would like to also welcome you all to visit us. So UTS is the building here. We are 20 minutes from the Opera House and the bridge, so it's a nice place to be. So when you think about your kind of quantum world or quantum information processing, there are mainly 3 applications that people discuss. So quantum sensing, driven heavily by the Diamond and Nitrogen Vacancy Center. Many groups pursuing this research, and you can refer to some references. And the idea here is that this defect is unique because it has a transition that's spin dependent, and you can essentially read out the spin state using purely optical and microwave means. So in a completely different regime, the development of quantum computing, and these applications are now becoming commercial very quickly, and they're based on the kind of superconducting qubits, and I'm not going to discuss this at all. And the third pillar of this quantum world is the communications, and I guess this is really how you communicate using purely single photon sources from point A to point B, maybe via the satellite, and the pioneering work here from the group of Jai Pan from 2017. And so when you think about kind of merging this quantum communications with quantum sensing and really try to realize quantum internet, you really need to kind of push it a bit forward and really think about, well, which source you can use that can be integrated with the photonic qubits, so with a photonic chain or photonic fibers, because photons are probably the most ideal means or the most ideal platform to communicate information. And of course, you also need some sort of a storage, so some sort of access to a memory, and you need to basically coherently manipulate and read out the information. And so when you look at this cartoon, what comes to mind is, of course, trapped ions. And indeed, the group of Rempe just published a very kind of basic, elementary, I should say, quantum network interfering between two trapped rubidium atoms just earlier this year, actually. They're separated by 60 meters, and so you can store the information within each atom and couple them to some sort of a cavity and then communicate by optical means. Now, of course, trapping ions is a bit hard, so we want to go to the solid state, and this work from last year from Derek England. So they chose a hybrid approach where they're using diamond as the hardware building block and aluminum nitride as the information carrier to interface with photons. And so here they managed to basically integrate about 16 nearly transform limited solid state spins that was based on germanium vacancy in diamond. There was no indistinguishability yet, but that's on the way to go. So this is a hybrid approach. And so it's kind of painting the picture of where the field is going in the next 5 to 10 years is basically to something like that, which is an integrated photonic circuit on a chip. And when you want to realize something like that, you need to think about, as I mentioned, quantum sources and memory access and cavities. And then it has to be nanofabrication compatible. And also you need some sort of tuning and manipulation mechanism. So the task seems quite easy, but actually very hard, because you will find very quickly that systems that have access to memory are not so good with photons, and systems that are very good with fabrication do not have any good single photon sources, etc., etc. So, as I mentioned, our group focusing predominantly on this quantum light sources, and we're focusing predominantly on HBN. And just before I dive in, I should probably explain what a single photon source is. So you can think about a solid state single photon source as analogous to a trapped ion, really. You basically have an artificial quantum system with a ground state and an excited state, which is buried very deep within the band gap of the material. So these defect states, these are your color centers in diamond, color centers in HBN and silicon carbide. And this is fundamentally a bit different than what we called excitons transitions or detuned excitons. And these are basically a very low energy traps just above or just below the valence or the conduction band. And these systems also can be isolated. So of course, the most common system is your epitaxial quantum dots. And more recently, with the emergence of 2D materials, you have the trapped excitons in WSE2 and WS2, et cetera, et cetera. And so the fundamental difference between the two is really the operation temperature. And so those systems operate mostly at cryogenic systems, and the defect states operate at room temperature. And so the first measurement that you would probably do in the lab if you studying these systems is an autocorrelation function, which means that you would split your signal into two detectors and measure correlation. And a dip here at 0 delay time means that you have no correlation at a specific time, which indicates that you have only one single photon source in your system. So you will see quite a few of those G2 functions throughout my talk. And these are just an evidence that they are single emitters. So I guess it's interesting kind of to go back in time to about 10 years ago. And in science, a decade can be actually quite a bit, but only 10 years ago, you would really only had two systems. So you would have the NV center in diamond. It has a very broad emission. So for many applications like communications or interference, maybe not ideal because there's not many photons in this coherent zero phonon line. And you had the arsenide-based quantum dots, which you would have already back then, you could grow very nicely into a pillar or a Bragg stack cavities, and you can generate very good quantum dots and plenty of groups doing this research. But fast forward 10 or 11 years, and now there's a whole library of different sources. So carbon nanotubes, perhaps the most recent kind of candidate of really reliable and bright sources. Quantum dots grew up immensely, and there are now commercial devices from people like Pascal and Allard, and also the group of Jabber Pan with Chai and Lu. And of course, single molecules have done tremendous work, and a field that we are interested in, which is the color centers. So the reason why we're interested in the color centers is, of course, the room temperature operation, that's one, but also it's a very robust system. And when I mean robust system, I mean, as a first-year graduate student, when you drop your sample on the floor, you can actually pick it up put it back under your confocal microscope and nothing really will change. So the defects are very deep within the band and protected by the lattice. So it's a very convenient system to work with. So where are 2D materials coming? And this merger between a kind of quantum and color centers and 2D materials is very not obvious. And I would just show you one slide, but hopefully it will provide enough motivation. So 2D materials are unique in this regard because you can make devices very easy. And this Lego style, this picture is quite old, but it's really powerful because you can really assemble devices and put them on cavities and put them on resonators, as was done by many groups. So here's one example where they put monolayer on top of a cavity. And when you think about fabrication, it really saves you a lot of time. And of course, it has a plethora of interesting effects. So the superconductivity in graphene you've heard, probably, I'm sure, and some other twist-based effects, which are quite nice. And if you want to move towards an integrated system with, for example, electrical excitation, then if you think about diamond, for example, making a PIN structure in diamond is very hard. But making a PIN structure in a 2D system is quite easy. You just exfoliate two systems and stack them together, and you would have an LED-based type. So, and this is where HBN comes into the scene. And if you look at this diagram of wide bandgap materials that can host these atomic defects, HBN is the only system that can really be exfoliated into 2D nature type. And so that is why we chose HBN. It has a very high bandgap, about 6 eV, and you can excite it with a green laser like you would do with your defects in diamond or silicon carbide. And of course, you can then assemble it into the devices. And I will show you a few examples. And so indeed, for HBN, there's been quite a bit of work already done. Also in the field of single photon sources, this is like a cartoon that emphasizes that, but also in the field of polaritons. So there's a lot of activities on polaritons. HBN supports polariton propagation, and it's a very interesting field of research. So I guess what I'm going to discuss in the next 40 minutes or so is really how do we go about defect engineering and emission control, and discuss a little bit about the origin of these defects, and then move towards integrated photonics and hopefully show you some spin properties and then summarize. Now, I think regarding questions, you can either chat, put in the Q&A, or you can just stop me and ask if you want. So both works. Okay, so we discovered this HBN emitters in about 2016, and since then there are actually quite a few works, and I just try to highlight as many as possible on one slide. And you can see that the field is really moving towards engineering them on demand, because unless you can engineer your single photon source on demand, you cannot really move forward with understanding what the system is and integrate it into the devices. And so many people use different techniques. There was some works done by putting HBN onto pillars, plasma-based systems. There was a very recent work from the group of Stephen Hoffman to irradiate or to anneal large HBN material and then kill some of the emitters with graphene that has apertures inside, and that creates this type of nice arrays. You can also make idents with an AFM, and also some approaches for ion implantation also work. So many different systems, and the defect structure is of course still unknown. And so that is how we started. We basically tried to grow HBN single photon sources by ourselves to try and control over the material fabrication and over the impurities. So we set up a very kind of naive system. It's not our idea of this growth. It's a tube furnace, standard tube furnace with ammonia-based and boron-based precursors. So the original growth is here by Lisong, again, almost a decade ago. But using this simple method, we can grow basically 1 centimeter scale HBN on copper very easily. It's a very bad quality material. So the material itself is bad. It's very polycrystalline. You can see it here. But nevertheless, the good part is that we can have emitters that are localized around 600, so 580 nanometers, and most of them are actually appearing in exactly this region. And they have a very sharp zero phonon line, as you can see here, and most of them are singles. So this was great, and this really shows you that we can control the material spectrally. And now that we can control the spectral, we can do very basic experiments, and I'm not going to go into details here, just to show you the powerful of the material. So as I mentioned, you can easily transfer it from the copper plate to basically any other substrate. So you can do then electric field modulation. So you can see here that the emission can be tuned by about 10 nanometers or so. Everything is at room temperature. This is just by putting it on ITO, done with collaboration with Oliver Benson. And you can also strain the material. And so again, you can put it on PDMS, and you can strain, and you can see here that there is a very large strain shift, about 45 MeV, a few nanometers, so about 10 nanometers, and the emission is very stable. So this is under strain and of course reversible. So it really opens up a lot of opportunities if you want to play with single photon sources for strain or for tuning, because you can now have a room temperature source that is stable, and you can transfer it onto any foreign device that you like. So moving on, we also wanted to have some sort of XY localization. And so here we try to grow directly on pillars. And there are two motivations here. One is, of course, creating this spatial localization. And the other motivation is to try and grow on dielectric directly. And so growing on dielectric is actually quite challenging, but very important if you then want to grow, for example, on a cavity, directly on a cavity. And so we made different pillars. I won't bore you with details, but somehow 700 nanometers works the best. And you can see here that just a confocal microscope of an array of 5 on 5. And so this is example of pillar number 17. It has a single photon source, very similar spectrum to the previous work here, grown on copper. And you can actually see remarkably that all the pillars basically show you this spread of around 600 nanometers as expected, and most of them are actually singles. So we now have spatial and spectral control. And an important point to make here is that there is not strain activated emitters, which means that there is no strain that affects whether they are formed or not. It's really a localization, most likely simply optical, because the pillars will just enhance the emission exactly at the top. Okay, so this is good. And so now you can really take the system and perform a little bit more detailed optical characterization to see how are we going towards a coherent source. And so here the results are really, really not so great, or I should say poor. So we can see a very narrow ZPLs, of course, but unfortunately, as you scan the laser, there is a lot of spectral diffusion. And so even though you can measure resonantly, you can excite them resonantly, when you tune your laser directly with your emitter, you don't see any Rabi oscillations. You would expect here in this G2 function to see Rabi oscillations, as I'm showing you here with my laser pointer, because this is a resonant excitation. And so the reason why this is happening is because you basically, instead of the emitter being excited and relaxed between a two-level system, the luminescence goes into one of these different trap states. And we are now trying to develop techniques to how to stabilize this. And I will show you one example in the next few slides. So the way to combat this spectral diffusion, and you can see it here, is really try to reduce the power to the minimum. And so this is now about 3 nanowatt excitation, again on resonance. And so now you can get a nearly coherent source, so 1.5 gigahertz. So our lifetime is about 100 megahertz, or we are only a factor of 10 away, which is already quite good. And so this is the line. It's still broadened, most likely phonons, but nevertheless, at least stable. So for some applications, 1 gigahertz is good enough. Obviously, if you want to do 2-photon interference, not quite there yet. So one way to increase your probability of getting these narrow lines and combating spectral diffusion is introducing what's called repumping. And so what repumping does is, in addition to your resonant laser, which is illustrated here, you put a second laser off resonance, so with the green laser here. And so the mechanism of why this works is actually still under debate. Most likely, under resonant excitation, you kicking out the charge state from the defect. And so if your defect has been, for example, a 0 charge state, by ionizing it, it becomes plus or doubly or negative. And what the green laser does is basically reinitializes the system. And so you can see the effect here. So we're doing a pulse green, and you can see that as we pulsing the green, we can start seeing the emission occurring. So this is in addition to the resonantly excited laser. And as we turn the green off, we basically see just the background. And you can repeat it again and again. And you can also change your repumping wavelength to see what's the best one. And so this is the probability to excite an emitter. So this is the probability to detect fluorescence, resonant fluorescence under resonant excitation conditions. And you can see that by repumping, we basically increase it by an order of magnitude. And so under this condition, you can actually record a resonant excitation spectrum, a properly coherent source. So, this is rare. If you going to the lab tomorrow to try this experiment, be aware that it only works on about 10% of emitters. We are not sure why, and this is what we basically studying now. Yeah. So the main question that we basically trying to address through all these studies is what are these emitters? And it's a needle in a haystack problem. Just our needle is not that big. And so here there are a few already examples of a lot of theory work actually on what can it be. And so our initial hunch was some sort of a vacancy-based defect, and then a recent theory suggests that vacancy-based defects would result in a very broad emission. So it is unlikely to be the case. But it is fully polarized, so it should be an in-plane defect, and also most likely some sort of charge conversion. So one of those charges probably more likely. Now, when we started to work on HBN, the immediate feel is, well, you have a 2D material, which is atomically thin. Why don't you just go to a high resolution TEM, find your defect and look at the defect? And so we all thought like that. And so it actually turned out to be very hard, because even though you can find the same spot that you did your photoluminescence from, and you can record also cathodoluminescence image from exactly the same spot as shown here, under the same exact magnification, you would have about 100, if not more, defects. And so one of them is shown here. It's a vacancy with an arrow, but you would have hundreds, if not more, defects. And this really heroic work was done by Faria Hai in Jen Dayon group in Stanford. And so you can do this correlation, and you can also map the strain fields, but you can never get a one-to-one single defect that is optically active to a single defect in a TEM. And so the other approach was, well, let's try super resolution imaging. And here, this is work from Alexander Aharonovich group in EPFL. And so what they did is they actually took a very well-defined triangular flake, and they imaged it down to about 10 nanometer resolution. And then they took the same flake into a scanning electron microscope. And again, within 10 nanometers, you would have quite a few defects. So this correlation, although HBN really offers an outstanding platform to correlate between TEM, STM, and super resolution imaging, it is still hard to really go down to the single photon level. But these techniques are now particularly appealing because for many years, people couldn't make a sample thin enough to really correlate between STM or SEM image, STM or TEM image and optical image. So we decided to kind of tackle it from a different side and really try to grow deterministically and pretty much eliminate everything else. And we started with carbon. And so carbon was proposed as a source of UV emission in HBN. And so what we did is, and don't worry about the details of the table, is we decided to grow HBN using metal organic vapor epitaxy, MOVP. And we chose this method because you could easily increase the carbon concentration. So you can go here from a very dilute sample to a very high sample, and TEB is just a carbon precursor. And so what we found is that as we increase the carbon concentration, we see an increased emission from HBN. And so this is an ensemble measurement. And as we go to a very low carbon concentration here, it's basically sub% or so. Yeah, so about sub% of carbon, you basically see no emission at all with a normal optical microscope. And so then we kick in our confocal microscope. And so then you can easily find a very isolated spots that are single photon sources. And remarkably here, that your ensemble measurement and your singles correspond one-to-one spectrally, which means that 90% or pretty much experimentally, it is more than likely that these are actually the same defects. Okay, so this is promising. And so you can, in a way, repeat it by ion implantation. So you can implant different regions, so masked and unmasked, and you can compare carbon implanted. You can see here after annealing, you see basically the same signature, and before annealing, you would see rather narrow lines as expected, and you can repeat it with oxygen and silicon and not see exactly the same features. So this is very convincing, and that carbon does play indeed a role. And the last evidence is really to look at this dose dependence. And so as you implant carbon more and more, so this is pristine flake, and this is 10 to the 11 to 10 to the 14, you can see that the concentration of this localized bright spot, which correspond to single emitters, is basically high, and you do not see the same thing when you implant oxygen or silicon. So this is a direct evidence that carbon is most likely the source of the single photon sources. Here a rather non-scientific, inspired by my kids, that if it walks like a duck and quacks like a duck, it's probably a duck. So let's just work on the assumption that we have carbon-based sources. Okay, so moving on to really integration of the sources with photonic devices. And so here, changing gears a little bit, we really want to mimic what's been done in the electronics domain and in photonics domain, and we want to be here. And this is a image that I adopted from the group of Yelena Vukovic in Stanford. And so you have here a photonic crystal cavity with a waveguide with a quantum dot integrated, and everything is nice and on chip. So how do you do it with HBN, or how do you do it with layered materials? There are challenges in refractive index. So for HBN, it's only 2, thickness, fab, etc., etc. And so we started this journey a few years ago, pioneered by Sejong Kim and Johannes. So Sejong is now a faculty in Melbourne University, and Johannes moved to the postdoc with Arka and Jadong in Washington. So what they did is they first really exfoliated a lot of HBNs and calibrated our optical microscope to know what is the thickness of the HBN based on color, because there is no point of making devices if your thickness is off. And so they could exfoliate exactly down to the thickness that is required, which is a couple of hundred of nanometers. And then you can easily pattern it with normal reactive ion beam etching. The undercut is achieved simply by putting this, these devices on top of a grid. So there's a question here. Could you further comment on the trap states, speckle diffusion? Yes, I would comment this on the end. No problems. So there is this. So you can make these photonic crystals, and you can see there is a cavity mode which is very low. For this, we need basically a little bit better design. So instead of having a 3D structure, we move to a 2D structure. We move to 1D. And in a 1D photonic crystal, you can easily get quality factors of about 2000, right at the 600 nanometer range. So this is this fundamental mode that is basically, we can tune it by just tuning the repetition of this leather cavities. So you can then move to holes. The reason to move to holes is just better confinement in the middle, so you can create your emitters. And so you can move here to 1D, but holes photonic crystal cavities. And now for the first time, we could actually see some sort of tuning. So you can see here, this is the cavity mode that we tune by just gas condensation. And this was the emitter here. And you can see, so this is cavity and emitter, and this is cavity and emitter on resonance. So with a Q of about 2500, we can already see a Purcell effect of about 10. And I guess one remarkable thing is we're doing this experiment at 70 Kelvin. And so, of course, we cannot generate indistinguishable photons at 70 Kelvin, but nevertheless, you can already probe your cavity engineering and your emitter tunability and stability at 70 Kelvin, which is very convenient because you don't need to drill holes for gas condensation in your expensive cryostats. You can just use a 70K cheaper cryostat. So that's where we're at in terms of cavity coupling. So we do observe Purcell enhancement, but it's still not entirely deterministic, which means that not every cavity really has a coupled system, because not every cavity has an emitter exactly at the middle. Okay, so how do we then kind of try to interface the whole thing? So we need some sort of waveguides. So we also made monolithic waveguides. So this is just a HBN monolithic waveguide. And so that's how they look. So we can make an emitter in the middle, and we can collect the light directly from that emitter. We can excite on one side and collect from one end, and we can excite and collect from the other end. So these are basically the middle, and this is C1, which is here. And this is the other end, C2. You can see that the waveguide is not ideal. We have a lot of losses on this end. Also, the spikes here are the Fabric-Perot resonators from the bouncing here within the waveguide. So there is a little bit of improvement to do, but nevertheless, the proof of principle is done, and we can really expand this structure into coupled ring waveguides and tapered fibers with photonic crystal at the end. And we even played with inverse design that I must admit straight away never worked. And even a beam splitter, everything is on chip. So you can see really here the exfoliated flake, very big flake with all the devices patterned on it. And this was highlighted on the cover of SES Photonics, I think just this issue. So we developed all these recipes for HBN fabrication. And in the step before, we developed all the recipes for emitter engineering. And so really in the next kind of, I think it's a year and a half, the group is really trying to push towards integration of this cross and the waveguides with the cavities together. So at the last bit, which I guess perhaps the most interesting bit for many of you are the spin properties of HBN, because it's not enough to have nice waveguides and nice single photon sources. You also need the defect with the spin. And so here, the story was actually quite interesting. So back in 2019, the group of Lee Bassett, they realized that some emitters show this magnetic field dependency. And what they did is basically they put the magnet and rotated the magnet, and they saw that the PL emission alternates. And so there was no optically detecting magnetic resonance, just a response to the magnetic field, which they explained based on a singlet and a triplet transition within the metastable state. So this is very similar to some molecules, for example. And so earlier this year, the group of Jörg Rachtrap, they actually found that subset of these defects in the visible range, so they call them D1 and D2, actually exhibit ODMR. And remarkably here, some of them show positive ODMR and some of them show negative ODMR, and only at cryogenic temperatures. And so the group of Mita Tature, they actually expanded this work significantly, and they showed that actually most of these emitters also exhibit ODMR at room temperature. So this is all at room temperature, and also managed to replicate this positive and negative ODMR charge states, ODMR signatures. So in this, interestingly, that both of these results support these carbon-related defects, most likely a trimer, C2CB or C2CN, with a very small ground state splitting. So this was good, but it's still not a spin one system, because you can see that you increase your magnetic field, but the peaks don't split, they just shift. So what we wanted ideally to find is a system that would exhibit basically an NV type ODMR with a large ground state splitting. And we found that after ion irradiations, that these emissions show a very large broadband emission at around 800. You may remember, you would actually have seen it when I showed you the silicon and oxygen implantation at this range. It was actually formed just because it was an ion hitting HBM. And what was remarkable is that when you scan your microwave around it, you would see a very pronounced peak at about 3.5 gigahertz. And as you apply magnetic field, here the peaks would split. So this is a perfect spin one system. And it was the kind of first ODMR signature at room temperature from HBN. This is still an ensemble. Now, because we could make these defects easily in an ensemble in a big crystal, we can actually do EPR on these defects and understand what they are. And so here is your triplet. So the first thing to know is that whether the split, the triplet here is the ±1 is above or below the 0. And you can do it by looking at high field EPR. So this is the high field EPR, and you can see that if the splitting behaves like this, The second peak will be much higher, which is experimentally verified. And you can also see that you have initialization for both basically the ZH and the ZL, which are these transitions, and this is the half field splitting. So the EPR is only available because we could make basically an ensemble, 10 to the 17, 10 to the 18 spins. So very large number of spins within an HBM crystal. Now, the other thing you can learn from EPR and ODMR is the hyperfine splitting. And so this really tells you what the defect is basically precisely. And so this is the experimental verification. This is our hyperfine splitting in EPR, and this is the simulated VB. So this is a missing boron surrounded by 3 nitrogens. And you can see here 7 peaks, matches perfectly. And if you would have put missing nitrogen with 3 borons, you would have had a very different spectra here. So it's a very clearly negatively charged boron vacancy. So there are a bit more details about the symmetry, how we figured out that it's a C3, it's a D3H symmetry, again from EPR. So now that you know that for sure you have a boron vacancy defect, and so it's easy to make those defects on demand. And so we just took a flake and basically, as I mentioned, irradiated with different ions, and you can see that we could make an array. And there, indeed, you can see this emission changes as a function of the ion. Intuitively, xenon is very big, so it will make very big damage. Therefore, the emission is not that great. But nitrogen is obviously very small ion, so it will knock off maybe potentially 1 boron atom, and you will have a much better emission creation here. Now, these emitters are very dim. You can see it here. The implantation dose is actually quite high, so we optimized it a little bit. It's important here that annealing is not required. In fact, if you anneal these samples, you would kill the boron vacancy, because the diffusion within boron nitride happens at about 200 degrees Celsius. So you cannot anneal them, which is a good thing, which means that you can just make defect where you want it. And so, but it's very, very broad and obviously very, very dim. And it's so dim that when you image here at the very dim sites with the hope of finding a single photon source, you actually do not see anything. So we still, after all these many attempts, haven't seen a single VB defect. And I will show you how we try to go about it. But nevertheless, so far, that's the only defect in HBM that we actually know what it is. So the first part of my talk, when I discussed the single photon sources, we don't actually know what they are. We have a good guess that it's a carbon related, and we can create them very easily and very bright, but we don't know what they are exactly. With this defect, it's the other way around. So we know what it is, but we cannot get a single. So to try and address this single thing, we can then go back to our cavity fab, and we can engineer these bullseye structures. And we chose bullseye structures simply because it's just easy to make, and they give you a factor of 10 enhancement or so straight away. And so this is our pristine here in the red HBN with a boron vacancy that we can create deterministically right in the middle, right? To just implant any ion with a focused ion beam. And we can tune the bullseye cavity and really put a resonance right in the middle. And we can enhance by a factor of 10 or so your emission rate, but unfortunately still no singles. So the other way to go is really going plasmonic gap cavities. And so here, this was inspired by work of Michael Mikkelsen and Stefan Strauff. And so you can, again, make an HBN, few layers, and put it on a gold and disperse cubes on top, and then achieve a very strong enhancement here within the nanoscale gap. And we've done it. And so here you can see that the coupled emission is enhanced by quite a bit. You can barely see the pristine VB. And this is the power plot. You can see that there is a lot of enhancement. But again, unfortunately, we have not measured any single photon emission from this defect. The ODMR contrast gets a little bit better. And here, in parallel, the group of Tonton Lee from Purdue, they actually went the other way around to enhance contrast. And so they actually made the VB and put it directly on the microwave antenna. and they immediately saw a contrast of about 40%. And so you lose some of your hyperfine information here because there is a lot of microwave power. But for some applications where you don't care about your hyperfine, you actually have a very good ODMR signal. So 50%, it's about 3 times as large as your NV center in the best case scenario. Yeah, and with the magnetic field, it splits as expected. So it's really, not only you can basically engineer these defects in atomically thin materials, but you can then also have a very strong ODMR contrast. So this work is really remarkable because you don't need to collect data for a long time. This contrast is really quite huge. So I think I would probably stop here and open it for discussion a little bit. So what I showed you, this engineering and control and some optical properties of the single photon emitters. I showed you some tuning, cavity engineering, and of course the spin-1 systems. So just to acknowledge the group, so this is in between our lockdowns in Sydney. So our COVID was kind of belated, and then 2020 was pretty much COVID-free, but last 3 months were COVID intense. So that's the group. Some of the people here left, and of course the collaborators. So just Vladimir Diakonov did all the spin manipulation and spin experiments on the boron vacancy. So we are not an ODMR experts, and also works with Oliver Benson, Weibo, Paul Barkley, Marcus Doherty, Alex Kubanek, and of course Takeshi Taniguchi from NIMS, who is, I think, a global provider of the best HBN materials. And thank you for your attention.
Thank you very much, Igor. This is a brilliant talk. It was very exciting to see all the different type of experiments you are doing, and new approaches also on integrated devices. I saw that one of the questions was actually placed by one of the QPI students. We will ask him to ask his question live. So Patricia can promote him so that he can speak and ask this a bit more, so that we don't have to read it, and we get to know Tiago Queiroz, who is a PhD student supervised in my and Pedro Apuim's group.
Hello, Igor. Can you hear me?
Yes, Tiago, perfectly.
Hi. So I'm also working in HBN, and I had a particular question. So you mentioned that the origin for the spectral diffusion behavior in HBN was caused by trap states in the vicinity of the HBN. Mm-hmm. And something that I've been considering is what would be the effect on spectral diffusion and the blinking caused by the environment of the HBN, specifically on defects very close to the surface of the layer. Would adsorbed molecules or dipoles in certain molecules in the atmosphere influence, and would we be able to measure this?
So you want to measure you want to use it as a sensor to measure the environment, or you want to measure basically a perfect source and you're asking how does the environment affect the source, or both?
Yeah, basically in order to achieve more controllable emission and more stable emission, what kind of manipulation?
So basically there are two problems here. One problem is the defects that are already in HBN, missing nitrogens, boron vacancies, interstitials, because the material is bad, and also your grain boundaries. And the second problem is what's happened with the environment, as you said, water and everything. So when we're going to cryogenic temperatures, we always cap our HBN. So even though we work with a few layer HBN, we always put another cap on top, so to prevent any contamination, or to minimize contamination before we put it in the cryostat. With regards to the impurities within the HBN, this is more problematic. So we tried this optical repumping, which seems to improve things a little bit. The other way you can do is you can try to control them electrically by Stark shift. We tried a few times, didn't really work, but there are a few works from Korea, from Jiwen Lee, I think, who managed to improve a little bit with Stark shift. But in principle, if you put electrolytes type or apply very strong field, you should be able to minimize this spectral diffusion. But of course, here the nature is against you because boron nitride has two atoms, is boron and nitrogen. So you will have a lot of things can go wrong. In this regard, diamond is a bit better. It's pure carbon. Yes, I hope that clarifies a little bit.
Yes, thank you.
Thank you very much. I just heard that Martin Lucas Garcia, group leader at INL and also panelist of the session, also has a question to you. Martin.
Thanks, Jana. Thanks, Igor, for the very nice talk. Well, actually, I have a couple of them, but to start with, I'm very curious about this, how you call it, the pre-pumping or repumping of experiment, right? That you did on the. So first thing is, this behavior you have seen only with the boron nitride, or this can be using other 2D materials, and also related with that, I can see that you get a much better efficiency at 500 nanometers excitation. Is there a reason for that, or? So
yeah, so the answer to the first part, actually, this technique is used for quantum dots and color centers quite often. So we stole it from them, as we stole many other things. So it works basically with any system. The reason why 500 nanometer works better than 532 or 480, we also went a little bit down, is actually kind of random. But what it probably tells you is it tells you where the other trap is. So if you think about this two-level, let me go back two more slides. If you think about other trap states where the charge can go, right, what the green laser does is it will reinitialize a charge exactly at your ground state so that when your resonant laser comes, it can promote it. And you need this reinitialization. So the reason that what the 500 nanometer tells you is that the trap that is most efficiently coupled to your defect is located exactly at about 2.5 EV from the grounds, from the conduction or the valence band where you promote and you ionize. So it would be different, of course, for every different defect. There is a very recent work now from Christoph Becker group in Germany on the tin vacancy in diamond, and they did a lot of the analysis on the repumping, and they actually found what is this mysterious defect that causes the blinking in diamond. So we haven't gone so far in HBN yet.
Okay, that's very interesting. If I may, very quickly, sure. Could I get your opinion on, also, you mentioned many different quantum single photon sources, no, at the beginning. What do you think about organic or single molecules? There are also some works, no, by Sandokan and Toninelli and on that, no? Can you comment on that?
Yeah, I can comment. So it really depends on what you want to do. So single molecules, if you can make one and you can really make it stable, it's perfect because it's like a trapped ion essentially. So it's a very defined transition. You know where it is. You can buy your laser. You can make a cavity around it, and it's really perfect. And you can even make more of those if you can make them. So it really depends on your kind of final goal. So single molecules, bright, very stable, but very hard to make. So indeed, as you mentioned, only maybe 2-3 groups can make a good molecular source. The other thing, it doesn't really have any access to spin. So spin manipulation is problematic. And it only works at cryogenic temperatures. So if you don't mind the cryostat and you have the ability to make the source, I think it's a very good platform.
Thank you.
Thank you very much for these questions and also answers. I am curious to learn a bit more about the approach to the integrated photonics that you mentioned. You showed a few fabricated devices, and as at INL, we also have a clean room facility with different e-beam direct laser writing. I was curious which materials you use, which processes you use, and maybe there are more questions still from the QPI students that also work with these technologies. And the question related to that is also, how do you model the photonic devices? What type of tools do you use there? Probably some FDTD description, or is this done mostly in collaboration?
So it's done now in collaboration, because we use FTTD numerical, just standard package. We had a postdoc in our group who is now has her own independent group, so Sejong Kim, and so she does the modeling mostly. It's a standard package, so we don't really innovate there. In terms of fabrication protocol, so here we use mostly, as you probably can guess, reactive ion etching and E-beam lithography. The interesting bit here is the choice of mask. So we're still playing around. So we use sometimes we use metallic masks that are a bit easier. Sometimes we just use the normal resist and normal mask. So like resist and liftoff. But we tried a few times directly with just putting a metal mask and etch through, which works quite well. We haven't done any fabrication with directly focused ion beam, which people sometimes do, just right with focused ion beam. So I don't know really about the damage distribution within HBN. We just don't have a good enough FIB in-house. And etch chemistry, mostly SF6, a little bit of oxygen, argon, but we don't have any chlorine in-house yet. So it's a very standard, basically fluorine-based etching.
Okay, thank you very much. I see there is Professor Pedro Apuim also having a question, having his hand up. Please, if you are able to promote him also to be able to speak and interact, that would be fantastic in the back office, so that Pedro can ask his question. Thank you.
Thanks, Jana. And thanks, Igor, for a very nice presentation. Can you hear me?
Yeah,
yes, we can hear you.
Okay, great. And my question was about the nanopillar structure. I didn't quite understand the structure and the way you manipulate the, I think the bornitride crystals, right?
Yeah. So
and you mentioned, sorry, you mentioned that 700 nanometers was working better, and this is the pitch, right, between the pillars, or what do you mean?
So so the pillars are made from silicon oxide, and what we do is we grow HBA directly on top. So we don't put the crystal on top, we just grow. So you can't see it from the image because it's conformal, but there is actually a layer of HBN here, and the 700 nanometers is the diameter of the pillar.
Diameter.
So, the diameter of the pillar, yes. And so the reason why, or our hunch is why this works the best, is because it's basically matches the enhancement of light properly. So 1 micron is probably a bit too much, too big, so it becomes like a flat bulk surface. And 300 nanometers is a bit too small, so it creates a lot of strain fields, and the HBN is maybe a bit strained. And so in this regard, 700 seems to work better. But it's very empirical study. So
and how do you grow the HBN without a catalyst here?
Yeah, so this is a question that we have been asked maybe 5 times during the review process, and now once again, and the answer is we don't know. So of course, with copper, it's very easy. You catalyze, and there's a decomposition, very well established literature. Without the catalyst on the electric, we don't know why
but it works. Yeah,
but it works. Yes,
and you work the same precursors that you would use for copper, right?
Exactly the same, and exactly the same temperature is a little bit higher, maybe by 100 degrees or so, but overall everything is exactly the same. And the HBN quality is worse, even worse than on the metallic structure. Of course, that's expected, but you have emitters. So the grain boundary is even smaller. It's about, we did some analysis, but it's about 100 nanometer grain boundaries, 200 nanometers, very small grain boundaries, but works.
Okay. Thank you very much.
Thank you.
Thanks.
Thank you very much. So this was another question from a research group leader at INF, the 2D materials and devices group. And now I see that from a theoretician, there will be a question from also research group leader at INF, from Joaquin Rossier. Yeah, he's part of the panelists, so I think you can just ask your question now.
Indeed. Thanks, Jana. And thanks, Igor, for the very interesting talk. Okay, I was wondering if it would be possible to figure out the identity of the carbon base defect doing some experiment with STM. My question is inspired by a slide you show in passing where you manipulate the energy of the emission of the single photon emitter with electric field, right? And you saw some tip, and I couldn't tell if this is an STM or an AFM or. But anyway,
yeah, we haven't done any STM. So there is a group in Singapore, Kaspersky and Costa Novoselov. They're doing some STM. The challenge with STM is similar to the challenge with TM, that in STM you would see localized defects, but you cannot correlate to the optical image, because optical is 500 nanometers. STM, you would see a defect every 100 atoms, so once per nanometer. So the correlation is harder. The other thing is that we tried actually a bit of STM with a few collaborators, and personally, we never even managed to get an image. So HBN is isolating, so we could never get a proper image. So most challenging part was always contamination, because when we transferred the HBN to the substrate that they wanted, like HOPG or something conductive, we would always have a lot of contaminations, and we couldn't really solve it. And so we just, how should I say, dropped the ball and stopped. But I think if you can do it properly, it would be terrific, terrific initiative, especially for the boron vacancy, because you now know what the defect is and we can create a lot of them. And so really doing STM analysis on this defect to start with, to see if you can actually see it, would be fantastic. Okay, I see. But the boron vacancy, you said this is not so emissive, right? So from the side of applications, it's not so interesting, or did I get that wrong? No, you got it right. So it's not that bright, but it has ODMR, which is the spin properties. So in this regard, it's even more interesting, because I'm just scrolling through. Yeah, because you can see ODMR. So this is a bad ODMR. Let me find a good ODMR. Yeah, so you can see very nice spin dependence, and you know the defect. So okay, thanks a lot. Yeah, excellent. Thank you very much. Before we close, there's one last question, and then we are closing the session. The question is from Christian Maybaum, staff researcher at INL in my group, in the ultrafast bio and nanophotonics group. Christian.
Yes, I hope you can all hear me, and thank you for the fantastic presentation, Igor. I'm not an expert on this, so my question is maybe very basic, but regarding the pillar structures, again, is the emission or the distribution of emission different from a flat surface? Is it more directional due to the pillar structures?
Yeah, that's an interesting question. So we couldn't really conclude it. So we did the measurement, we did a backfocal image to check the emission, but it wasn't really that conclusive. And partially it may be because the emission is already oriented in a specific way, and we work with a very high NA objective. So we probably already collect the light in the same kind of collection angles from the surface and from the pillar. So it's hard to say if it's more directional, but it is definitely brighter. So it's about 2 to 3 times brighter than if you would have collected from just a normal plain substrate. So there is definitely an enhancement in this regard, but directionality-wise, we don't really know.
Okay, thank you.
Thank you very much. Thank you very much to Igor, of course, for this excellent talk, and thank you for everyone who participated in the question and answer session. We hope, Igor, you will indeed come to INL soon, once possible. So there's a lot of interest from different research groups, and we are, it's quite exciting that there are so many synergies possibly, or joint interest in these materials and in quantum photonics, of course. Thank you so much. We say goodbye. And
thank you, and thank you for hosting. And of course, if there's any collaboration opportunities, we would welcome pretty much everything. So just flick me an email and we can discuss it offline.
Excellent. Thank you so much. Goodbye.
Thank you. Bye-bye.